Yes, welcome to this fifth semester, dear students. So, you have come into the fifth semester, basically, which contains the two papers in all the optional subjects, paper 1 and paper 2. So, I am going to teach about the topics that are present in the paper 1. So, the syllabus of this semester is the coordination chemistry, that is paper 1 in organic chemistry. In this, you have review of the terms like double salts, complex compounds, central metal ion, ligand, coordination number, and complex ion. And you are also going to study about the classification of ligands, Werner's theory of coordination compounds with reference to cobalt-amine complexes, IUPAC nomenclature of coordination compounds, calculation of effective nuclear effective atomic number in a different complexes, stereochemistry and complexes of coordination compounds with coordination number 2, 3, 4, 5 and 6, ionization, hydrate, linkage, geometrical and optical isomerism in coordination compounds with respect to coordination number 4 and 6. So this whole topic carries 7 hours. Then you have another topic called organometallic chemistry. In this, you are going to learn about the classification of organic transition metal complexes, metal carbonyls, bonding in metal carbonyls, 18 electrons and 16 electron rules with respect to metal carbonyls, synthesis, structure, bonding and reactions of metal alkyl complexes, which carries 4 hours of duration. The third topic in this is metal clusters, carbonyl clusters and halide type of clusters. These are the two types of the metal clusters. Examples and structure of low and high nuclearity carbonyl clusters. Example and structure of halide type of clusters, which carries 3 hours. Now coming to the coordination chemistry 1. In this coordination chemistry 1, you have already studied this topic in second year PUC. Now to start with this coordination chemistry, how this coordination chemistry has started. It has started in two ways. One is based upon the bond and another way is the discoveries. Now coming to the types of bond, which you have already studied these bonds in the earlier semesters. So we have the 6 types of the bonds like ionic bond, covalent bond, coordinate bond, metallic bond, hydrogen bond and van der Waals force of attraction. Now among these bonds, the first 4 bonds are stronger bonds and the next 2 bonds are the weaker bonds. Now let us restrict our study to coordinate bond. So the ionic bond is formed by transfer of an electron from one atom to another. Covalent bond is formed by sharing of unpaired electrons between the two atoms. And the coordinate bond is formed by donation of a lone pair of electron from one atom to another atom. Now, in this case, an atom, it donates a lone pair of electron which are responsible to form a bond. Now, these atoms generally have lone pairs of electrons. The atoms which donates the lone pair of electron from one atom to another is called the donor, and the atom which accepts the lone pair of electron is called the acceptor. Generally, the transition metal ions acts as acceptors. Therefore, we can define a coordinate bond as a bond between the two atoms by donating a lone pair of electron from one atom to another. This coordinate bond is represented by an arrow mark from donor towards the acceptors. The compounds containing coordinate bond are called coordination compounds. The study of these coordination compounds is known as coordination chemistry. This is one way of how this coordination chemistry has started. Now there is another way called the scientists were interested to study about by mixing the two simple salts. Now during these studies, they were just mixing the two simple salts and they used to get the double salts. The double salts, they have a different property than the two simple salts. For example, if you take ferrous ammonium sulfate, this ferrous ammonium sulfate is formed by mixing ferrous sulfate and ammonium sulfate. Ferrous sulfate is light green in color, ammonium sulfate is colorless. These two salts are taken and they are added in the water and evaporated slowly to remove the water to get the crystals of ferrous ammonium sulfate. This was first observed by the scientist called the Moore. Hence, this ferrous ammonium sulfate is also called Moore's salt. This Moore's salt, the ferrous sulfate, why the scientists were interested to prepare such double salts? Because these double salts, they have different physical properties than the individual salts. For example, as I have said, the Moore's salt, which basically contains the ferrous sulfate. The property of the ferrous sulfate is it easily gets oxidized to ferric sulfate. Just by mixing ferrous sulfate with ammonium sulfate, the rate of oxidation decreases enormously. Therefore, the ferrous ammonium sulfate is having a different physical property than either the ferrous sulfate or ammonium sulfate. Therefore, the scientists were interested to prepare such double salts. Then we can define the double salts are those molecular or addition compounds which lose their identity in their solution and they have a different property than in the solid state. The meaning of this is, if you take ferrous sulfate, as I have said, ferrous sulfate is having an oxidation property. It readily gets oxidized. But with the presence of ammonium sulfate, rate of oxidation gets reduced enormously. Another property of the compound is potash alum. If you take a potash alum, which is nothing but a double salt formed by the reaction between aluminium sulfate and potassium sulfate. It is K2SO4, Al2SO4 thrice, 0.24 H2O. Alum means which contains 24 water molecules as water of hydration. Here, this potash alum is having an entirely different property. It is having a coagulating property and also it acts as an antiseptic in solid state. But it loses its property when it is dissolved in water. So therefore, the double salts are those molecular or addition compound which loses their identity in solution. The scientists were interested to prepare such salts, and these salts, they give all the ions that are present in them when they dissolved in water. That means if you take ferrous ammonium sulfate, which contains ferrous ion, ammonium ion and sulfate ions, in solution it gives the test for all these radicals. Similarly, if you take potash alum contains potassium ion, aluminium ion and sulfate ions. In solution, the potash alum gives the test for all these radicals. So keeping this point in view, the scientists were interested to prepare the number of double salts. And during this time, one of the scientists, he wanted to know the poisonous character of potassium cyanide when it is mixed with ferrous cyanide. We know potassium cyanide is deadly poisonous. So when he mixed potassium cyanide and ferrocyanide and he observed the compound that is formed, it shows an entirely different property even in solid state as well as in solution state. For example, as I have said, potassium cyanide, when it is mixed with the ferrous cyanide, we get potassium ferrocyanide. This compound in solution did not give the test for ferrous ion as well as the cyanide ion. It used to give only the test for potassium ion. Then the scientists were thought why it is happening like this. So there they could not explain where this ferrous ion and cyanide ion gone. So therefore, since they could not explain properly, they called these compounds as complex compounds. And later on, they came to know the complex compounds are nothing but the coordination compounds. So that's how the history of the coordination chemistry. Now coming to the complex salts or coordination compounds, both meaning is the same. We have today the plenty of coordination compounds. These coordination compounds have very wide applications in biological systems. For example, iron is very essential for the body, but iron cannot be taken as ferrous sulfate or simply iron in solid state. So this iron is present in the form of a complex compound. So those compounds, when we take through the tonics, so the iron assimilates in our body and gives the iron content in the blood. So these coordination compounds have like this very wide applications in various other fields. Having a brief account of the formation of complex compounds or the coordination compounds, now let us study about what are the various terms that comes in coordination compounds. Now the terms in coordination compounds are the first one central metal ion, next ligand, third one is coordination number, and fourth one complex ion. I have taken here three examples. So the first one is called CuNH3 4 times SO4, which is called cuprammonium sulfate, K4FeCN6, which is called potassium ferrocyanide, and then CONH3 6 times Cl3 hexamine cobalt 3 chloride. Now let us discuss the above terms with respect to these coordination compounds. Coming to the first one, the central metal ion. The central metal ion is a transition metal ion which accepts the lone pair of electrons So because these transition metal ions, they have vacant d orbitals. Therefore, in case of cupramonium sulfate, copper ion is a central metal ion. In case of potassium ferrocyanide, the iron Fe in +2 state is a central metal ion. So in CONH3 6 times Cl3, cobalt 3 plus ion is a central metal ion. The next comes the ligand. The ligand is an atom or a molecule which can donate a lone pair of electron to the central metal ion. I repeat, the ligand is an atom or a molecule which can donate a lone pair of electron to the central metal ion. So, in the above examples, ammonia is a ligand. In case of cupramonium sulfate, cyanide ion is a ligand. In case of potassium ferrocyanide, and ammonia is a ligand in case of the cobalt complex. And all these ligands, they donate only one lone pair of electrons to the central metal ion. Hence, these ligands are also called monodentate ligands. Monodentate means they donate only one lone pair of electrons to the central metal ion. Coming to the third term, that is coordination number. Coordination number is nothing but it is the number of monodentate ligands attached to the central metal ion, or in other words, it is the number of lone pairs of electrons given by the ligand to the central metal ion. In case of cupramonium sulfate, 4 ammonia molecules are attached to the copper ion, hence coordination number in cupramonium sulfate is 4. Similarly, 6 cyanide ions are linked to the ferrous ion, therefore coordination number of Fe2 plus is 6. In a third example, 6 ammonia molecules are attached to cobalt ion, therefore coordination number becomes 6. Now coming to the another term called the complex ion. So the complex ion is nothing but it is a charged ion containing a central metal ion and the known number of ligands. And this complex ion is always written in a square bracket. Now, in case of cupramonium sulfate, CuNH3 4 times 2 plus, this becomes complex ion. This complex ion is a cation because it carries positive charge. In case of potassium ferrocyanide, ferrocyanide ion is called a complex ion which carries 4 minus charge, and it is an example of anion complex ion. Coming to the third example, CONH3 6 times 3 plus is once again a cation complex ion. Lastly, I have given an example called COCl3NH3 thrice. This complex is a neutral molecule because in solution it will not dissociate into positive ions and negative ions. So this gives a clear picture about the various terms that are present in this. Now, to explain this, I have given some of the examples also here, as I have said earlier. Double salts, I have given the various examples like Morse salt, potassium and carnallite. Carnallite is KCl MgCl2.6H2O. So this is also an example of double salt. Now, In case of coordination compounds, we take some of the other examples like nickel NiNH3 4 times 2 plus. So when I take NiNH3 4 times 2 plus, so in this NiNH3 4 times 2 plus, so the ammonia is a ligand where the coordination number becomes 4 and nickel is in plus 2 oxidation state. There is a one more ligand, the nickel complex, that is NiNH3 6 times Cl2 also. So in NiNH3 6 times Cl2, it is called hexamine nickel 2 chloride, which undergoes dissociation to form hexamine nickel 2 cation and 2 chloride ions. So this becomes a complex, nickel becomes a complex ion. Now the coordination number becomes 6, ammonia is a ligand, nickel is a central metal ion. Similarly, this we take another example, the potassium dicyanoargentate 2. So in this potassium dicyanoargentate 2, silver becomes the central metal ion, cyanide is a ligand, and the 2 becomes the coordination number, and dicyanoargentate, which is written in the bracket, becomes an anion, complex ion. Now, as I have given the other examples also in this particular the slide. So here also I have given the complex ions and how they undergo the dissociation. Now here I have shown about the coordination and complex ion, central metal ion with various examples. Here charge on a complex ion is also written. This also I have told you, if a complex ion carries a positive charge, it is a complex positive ion. If it carries negative charge, it is a complex negative ion. Now the later on, with the next we take the ligands. As I have said, the ligand is one which donates a lone pair of electron to the central metal ion. If the ligand donates only one lone pair of electron, it is called monodentate ligand or unidentate ligand. Examples: ammonia, water, chloride ion, bromide ion, cyanide ion, hydroxyl ion and nitrite ion. Even the carbon monoxide also acts as a monodentate ligand. Now, a ligand which donates two lone pairs of electrons to the central metal ion is called bidentate ligand. Now, we have various bidentate ligands like oxalate anion. So, we have dimethyl glyoximate anion and ethylene diamine molecule. Now, in all these cases, so in case of oxalate ion, oxygen acts as a ligand. It donates a lone pair of electron. In case of dimethyl glyoxime, the nitrogen and oxygen donates a lone pair of electron. Like this, we also have tridentate ligand, tetradentate ligand and even hexadentate ligand, hepta and octadentate ligands. So ethylene diamine tetraacetic acid is an example for hexadentate ligands, and all these ligands are generally referred as polydentate ligands. This is one way of classification. So here this table shows various other examples of monodentate, bidentate, tridentate, tetradentate, pentadentate and so on, and their structures. Students, you must remember the various examples of these types of ligands. So This is a basic class to know about these aspects. In the next class, let us we study about the theories of coordination compounds. In the theories, Werner proposed for the first time to explain about this coordination compounds. In the next class, let us we study about the Werner's theory of coordination compounds in detail. Thank you.